Welcome back to the channel. I'm Adam Pease, and today I want to talk about the topic of negation by failure. I'll explain what that means. So let's say there's a fact that it isn't explicitly true or false. I don't know it for sure. And I'm asked if that fact is false. What do I say? Let's take two particular examples of this. Maybe first an outrageous question. Is there a rhinoceros in the other room? And your answer presumably would be, of course not. And maybe your interlocutor could say, are you sure? Have you looked? And of course, that's silly. We just know as human beings that unless we happen to be working at a zoo, this is ridiculous, right? We don't know for sure, right? We haven't, say, looked in that room in the last second. And so maybe a rhinoceros really has appeared in my living room, but I can be pretty sure it hasn't. So it's a fact I don't know explicitly is true or not true, but I have assumptions, I have common sense, I know some things about the world, and so I give an answer. And then let's take a second example. Are my keys in this other room? Well, I don't know. It could be. I don't have enough information because I could drop my keys anywhere after I come in from doing an errand, and I just don't know the answer. I don't have information, and so I say I don't know. So completely different common sense context, but from a computer's perspective, these are both facts that I don't know to be true or not true. And how should a system, an automated system, handle this problem? What's the right default answer for our machines that don't have all the necessary information about the world? So there's two different possible systems that I'd like to introduce today. So one is strict first-order logic. And we use, in the work that I do, the TPTP language that's been, the creation of which has been led by Professor Jeff Sutcliffe at University of Miami. And I'm going to show today a popular theorem prover written by Stefan Schulz, who's a professor in Germany. And he has a prover called eProver that's consistently one of the top provers. And it'll certainly be sufficient for this little test problem that we have today that I have formalized on the left in just four statements at the top. On the right, we have Prolog. And Prolog was very popular in the sort of first big wave of artificial intelligence. It's not so familiar to a lot of people now, but it's probably more familiar, arguably, than a lot of the strict first-order logical languages. Prolog is a sort of hybrid. It's a logic programming language, and so it includes both declarative aspects and procedural aspects. It's a bit of a hybrid, and it's formalized with these four statements on the right. Now, fortunately here, they're both sort of vaguely Prolog syntax, so if you're familiar at all with Prolog, you just have to do a little bit of a mental switch to read programs in the TPTP language. Most notably, the direction of implications is switched. So in Prolog, if we have, for example, X and Y are unrelated, we read this, I can conclude that X and Y are unrelated if I know that X is not a sibling of Y. Whereas in TPTP, the arrow goes in a different direction, if you will. If I know that something X is not a sibling of Y, then I can conclude that X and Y are unrelated. Right? So in this simple problem, we have only one fact, that individuals that share a parent are siblings. We have two facts about the parent of Billy and Sally being John. And then we also have the rule that, take it just for this example. Of course, it's not sufficient for real life, but that if two people are not siblings, therefore they're unrelated. Because in this little example world, we only know about the sibling relationship. And so what we're going to try to ask is some different questions to see how standard first-order logic and Prolog-based logic programming give you different answers when you don't know something about the world. So in particular, they can both answer easily that Billy and Sally are siblings, because we have this rule coded in this slightly different syntax for both languages that if two individuals share a parent, they're siblings. We have the same fact, we have the same rule, in both languages, easy to conclude. We also have the same lack of conclusion for asking whether Billy and Sally are unrelated. Billy and Sally, we don't know that they're unrelated because in first order logic, we don't have the fact that they're not siblings. Or we know that Billy and Sally are siblings, but we don't have a fact that says the opposite. And we don't have any rule that tells us if I know some predicate is true of X and Y, then it is not the case that the opposite is true. Right? We don't have that anywhere. So we just don't have this not sibling X of Y anywhere that would help us understand what's going on here. And similarly, we don't have that on the Prolog side either. We then have the option of asking another question. Let's try asking a question that's maybe more aligned with my introduction a moment ago. Let's ask about Bill and Bob. Well, we have no information about Bill and Bob. We only know about John, Billy, and Sally. And so if we ask, are Bill and Bob siblings? Well, no, we get no answer. The logic program, first order logic, has no way to conclude that Bill and Bob are siblings. And neither does Prolog. But even though it has no information about Bill and Bob, remember that Prolog gives you a definite answer. It's going to give you a definite answer. If I don't know something, I therefore know it's not true, is the way to think of it. So because in Prolog I don't know that Bill and Bob are siblings, I can conclude definitely that this is false. So a much stronger commitment than you get out of first order logic. Is that the right choice for modeling reality? Well, it's just a model, so there isn't a right answer. Prolog does it one way, first order logic does it another way, and it's up to you to figure out are either of these good models for the world. And of course, a third model would be some sort of probabilistic representation. But if you don't have information about what's the probability that two people are siblings, you're left in the same situation. So there isn't a magic answer to this. There are just different ways to go about modeling it. The hard part is, how do we collect all this knowledge and get it into the computer in some form? And here are just two options for a particular form of encoding information about the world. Now, it's the last example that I think is the most interesting. Here we ask, are Bill and Bob unrelated? Well, again, we know nothing about Bill and Bob, so therefore we know no facts that could allow us to conclude other facts, and so the search procedure of automated theorem proving just says no proof found. I've tried everything I can try, and I can't find an answer for you. Prolog, however, gives you a different approach. So I ask if Bill and Bob are unrelated. How do I find out if Bill and Bob are unrelated? I find out by determining that one is not the sibling of another. But notice from this previous example, if I don't know that Bill and Bob are siblings, I can therefore conclude in Prolog that they are not siblings. Great. Now I have that Bill and Bob are not siblings, therefore, incontrovertibly, they are unrelated. And so Prolog, again, gives me a definite answer. It says that, yes, indeed, Bill and Bob are unrelated. Okay, so now let me do all this again live in a demo using a theorem prover for first order logic and a version of Prolog. So let's look at how we would want to execute these statements to demonstrate the difference between Prolog and standard first order logic. So here on the editor I have the TPTP version, first order logic, and then on this side I have a Prolog version. So one thing to make note of is that the Prolog rules have the result on the left-hand side, you might say. So the notion of sibling X of Y is created or asserted when we meet the conditions of having that Z is a parent of X and Z is a parent of Y. And the notation for TPTP, which is a standard Prolog-like syntax, for first order logic, it's actually the reverse. So here you can see that we can conclude that the sibling of x is a sibling of y if these following conditions are met. That for all x, y, and z, that z is a parent of x and z is a parent of y. Okay, so let's try starting with the first order logic version. So here we're going to say ask a query. Let's start with our first query, that whether Billy is a sibling of Sally. Okay, so we save this, we go over here, and I've already queued up the statement with all the right options to execute the E theorem prover. And note here that we're executing nbf.tptp. That's the file we've had on the right. And we execute, and it's super fast because, of course, there's only 6 statements here. So if we look up past all the statistical results, you see we actually do get a proof. So we have proof found is the conclusion amidst all this stuff, which if you're not familiar with it could be a little daunting, but we're looking for the SZS status, that it is a theorem. We found a proof. And then we're provided a step-by-step proof going from the conjecture is Billy a sibling of Sally. We go through 12 different steps. Most of the steps are just actually transforming the input as opposed to really doing any new conclusions. There's not much that we have to conclude here, right? We have to find that in order to determine whether two things are siblings, two people are siblings of one another, we have to conclude, we have to find out that Z is a parent of one and Z is a parent of the other. And so we can find that out because of these 2 facts here, that both John is a parent of both of Billy and Sally, and then we get the conclusion, right, of this query that we've asked. All right, so that's the TPTP version. Let's take a look at the Prolog version now. So we'll open a new window. We'll open SWI Prolog, which is a standard, friendly, open source Prolog that runs well on Linux, as well as I believe other operating systems. And let's load the file nbf. Okay, so load that. It says true, yes, it's loaded, and we can ask this same query. Sibling Billy Sally. And we get true. Okay, Prolog's a little different, and well, a lot different in many ways. It's not giving us a proof, it's just giving us the answer. We could do a trace and step through it, but it's executing a program, it's a logic program, as opposed to just a statement of a lot of facts and doing a search through those facts. It has a procedure for interpreting those facts, but it's somewhere in between a logic and a programming language. All right, so let's go on to our second statement. As to whether Billy and Sally are unrelated. Now, common sense would say, well, of course, you and I know that siblings are not unrelated. But the program, as the way we've stated it, actually doesn't have enough information to give us an answer. So let's try this. Unrelated Billy Sally. Okay, and we get false back. And let's take a look at this program to see how we can determine that we're not getting an answer. Right? So in order to determine unrelated, here, 2 things are unrelated if it is not the case that one is the sibling of another. But we don't know that it's not the case that one thing is a sibling of another. We only know that it is the case that one is a sibling of another. So we know that if John is the parent of Billy, John is the parent of Sally, that satisfies these 2 conditions, that we conclude that Billy and Sally are siblings. But we don't know that they're not siblings unless the program actually says that explicitly, and it doesn't. So we don't have a way to get an answer. So let's also take a look then at the TPTP version. Same set of conditions. right? And we'll go back to this window, and we're gonna, let's see, we're gonna want to show that they are Billy and Sally are unrelated. So before we were able to conclude that they're siblings, and we conclude that they're unrelated. So I save that, go back over here, I execute the E-theorem prover on the same file, and what do we get? We get a bunch of statistics. Let's go up. Now we're getting saturation, okay? And notice here we're not getting a proof, right? We're just getting a listing of the different things that it's tried, but we don't get actually a proof. We don't get false. We don't get a contradiction, which if you watch one of my other videos, that's the key thing. We're doing proof by contradiction in this logic. So we get instead no proof found. It just saturates, and saturation means it's just tried everything it can try. Tried every conclusion, sub-conclusion, all the search paths that it can in this tiny little theory, and it can't find an answer. And that is what we would expect. All right. So let's go on and try to see if we can ask some other questions. So sibling of Bill and Bob. Now, of course, we don't have any information about Bill and Bob. We have some rules, but we haven't included those other constants anywhere. We're just going to ask a question about them. Now, let's see. So we'll go through here. We'll run E again. Okay. Oops. Let's make sure we save it. Okay, and what do we get? We get, again, no proof found. We get a bunch of information there. There's information about Sally and Billy and stuff, but nothing about Bill and Bob, so we just don't have enough information to conclude anything. Let's try the same thing now in Prolog. Here we've got the same file. We've got an interactive prompt, so we can go a little bit faster. So we can just simply ask this as opposed to having to edit the file and save it. So let's see, Bill and Bob. Are Bill and Bob siblings? No. Now, a key thing here, note that when we run the Prolog program, it gives us this definite answer that, in fact, they are not siblings. Whereas all that the TPTP side, or the E-theorem prover, is telling us is that there's no proof found. Right? It's a I don't know kind of answer as opposed to a yes I know and it's not true. Right? So let's go on to our last thing here. The last thing we want to ask is if Bill and Bob are unrelated, and this will make things quite a bit more definite for us as an illustration. Okay, so here Prolog is telling us definitely Bill and Bob are unrelated. And the way in which it does that is that it knows something is unrelated if it is not the case that one thing is a sibling of one another. Okay, very simplified rule set. Obviously, this isn't true in real life, but take for granted this theory here that we've developed just for illustration. And what Prolog is doing here, it says that if I don't know that X is the sibling of Y, then I can definitely conclude that X is not the sibling of Y. Right? If I don't know it, it's not true. So it's a very confident sort of program. So that's why it tells us that indeed Bill and Bob are unrelated, definitely. Whereas if we try this in TPTP, we want to ask if unrelated Bill and Bob. So we're going to save this and go back to our TPTP window. We're going to execute E on this same program again, and what do we get? We get, similarly, no proof found, because there's no way that it can determine anything here about Bill and Bob being unrelated, because it doesn't know that they're not siblings. And this fact here has to be present for us to conclude this other fact, whereas Prolog takes the opposite approach that says, if I don't know this, if I don't know that X is a sibling of Y, or Bill, specifically Bill is the sibling of Bob, I conclude that definitely that Bill is not the sibling of Bob. Once I've concluded that fact, a host of other things could follow from it. And in this case, in this very simple theory, it says that indeed Bill and Bob are unrelated. So very different outcomes. In one case, we've got no proof found from a strict first-order logic system. And in another case, we get a definite answer. It's true that Bill and Bob are unrelated from our Prolog logic program. Another way to talk about this is in terms of what's called the closed world assumption. So Prolog makes this assumption that the world is closed, that you know everything that is true or false in the world. And because of that, it can be very efficient. Instead of searching for answers, and especially in the what you might call the deductive closure of all the rules you have, it just says if I can't find it, it doesn't exist, therefore it's false. That makes Prolog very fast. First-order logic, in contrast, will keep searching for an answer even if none exists. It doesn't have always a way to fail quickly. But it has what we call an open world assumption, that there might be something that is relevant to the particular problem you're working on that simply hasn't been stated. And so the safest thing is to just say, I don't know. And the practical fact here is that with software, with computers today, we can't specify everything we don't know, and we also can't specify everything we know. So we have to figure out a compromise that makes practical reasoning possible in software. There are, however, some additional compromises here. You can do a closed world assumption, say, on a particular predicate, a particular relationship, and say that maybe with some kind of meta predicate that company membership is a closed relationship. So presumably if I own a company, I know everybody that works for that company. I'm signing the paychecks. So that shouldn't be the case if I say, is Bob a company member, that I don't know. Either he's on the payroll or he's not on the payroll, and I should be able to fail fast if I don't find a Bob on the payroll as opposed to just saying I don't know. And conversely, if I ask, is Abraham Lincoln on the payroll? Well, if he's not listed on the payroll, I should be able to absolutely say no. So this is one way to handle it without making a blanket commitment to either the open world or the closed world assumption. So that's a quick introduction to negation by failure and the closed world assumption and the open world assumption, and I hope this was helpful and interesting to you, and if so, please like, subscribe, comment, or check out some of the URLs that I have listed here. Thanks very much.